Hi, this is Mort from PCAndVR with a video demonstrating augmented reality using Vuforia libraries on builds for Android using Android Studio and Unity 2017.2. If you're not familiar with augmented reality, or AR, it means using a device to synchronize virtual objects into the sensory field, for example, visual or auditory, through which we experience the real world. A key feature of AR is locking a virtual reference frame into a live camera image of either a specific image target, a 3D object, or a surface or ground plane. This reference frame becomes a stable center point for generated 3D objects to exist such that they appear synchronized with the real world in the device's camera image. Because an AR object or image target can be tracked in 3D space, it actually provides a form of head tracking for mixed reality XR if you use a mobile virtual reality VR head mount with a camera opening such as Samsung's Gear VR or custom Google Cardboard headsets. Without head tracking, VR headsets can only provide 6 degrees of freedom rotation from a single point and no translational movement in virtual space, adding to motion sickness. AR devices can be something as simple as a recent model mobile phone or tablet with camera. Head-mounted AR devices can be more useful for hands-free operation and keeping virtual objects in the field of view, but typically there are weight and portability issues with tethered head-mount devices and image quality limitations on current untethered glass frame devices. This video will demo 3D AR object tracking using image target and virtual buttons, as they are reliable and simple to implement. First up, we have the Android Studio built app, which largely contains the same feature set as the Unity app, albeit using simpler models and older image targets. The first Android Studio example uses the stones image target. The added 3D object is a teapot, originating from the famous 1975 Utah teapot 3D model. Using the app, we can show the teapot from various distances, angles, and even zoom in on the inside of the spout, with the teapot visually appearing fairly stable against the stone's image target. The image targets are printed on A4 paper from files in the supplied library and are designed to be high contrast, with numerous well-defined edges and non-repeating features. This allows detection and tracking even if only a portion of the image is visible in the camera field. The second Android Studio example uses the wood background image target with 4 virtual buttons. Each button gets mapped with a virtual rectangle surrounding it to detect occlusion by real-world objects, effectively meaning the button has been pressed. In this case, it changes the color of the teapot to match the color of the virtual button covered by my fingers: red, blue, yellow, and green. Next, we move to the Unity build of the same type of example features with image targets and non-interactive 3D objects, and virtual buttons to allow interactive 3D object behavior using the same image targets. Here we have a standing astronaut, which can jitter if the AR device is not held steady, an effect worsened by the model's height and relatively small target image size. Next is an oxygen cylinder, which is significantly more stable due to the 3D model being smaller and positioned closer to the target surface. And an animated drone, which, while small, can jitter in the hovering position above the target surface. I coded a custom 3D image of my own showing an empty game level platform using the stone's image target and downloaded XML file, but I could have used any suitable custom image with the Vuforia web XML generator. Finally, the Unity build's virtual buttons feature shows the astronaut waving after a button press, the oxygen cylinder displaying an infographic drop-down visual, the drone emitting a blue projection field, and the fisher changing from white steam to dark red In concluding, we saw some limitations of smaller, less complex image targets in terms of feature detection and target tracking, with resultant visual instability of mapped 3D objects worsening further above the surface of the target, and objects disappearing at low incident angles to the target, where feature detection is not possible. Both these limitations can be mitigated somewhat through use of 3D object targets or larger complex multiple image targets on 3D objects, since the detection should still clearly see features of one target, even if those of another become occluded or at a low angle. For further background info and links, please see the transcript for this video. And that's it, so thanks for watching.